So this is the second video of the formation of the elements. And so in the second part, what I want to do is kind of get back to this idea of creating all the elements in the periodic table. And so at this point, we've really only gotten to iron, which is atomic number 26. So it's a little blurry, but again, you have these PowerPoints. And iron 56 in that mid blue section is right in the middle of that top row. So there's lots of elements to go in terms of creating stable nuclei. And so where we left off was a star, a red giant with a iron core. Once iron forms, there's no gain in energy through fusion. So at this point, there's no expansive force. It was that heat of fusion that was battling the gravity, pulling in the mass of the star. And so without that expansive force, the star collapses. And in our scenario, in terms of creating the heavier elements, we are going to have a supernova explosion. Again, when a star collapses, there's many different avenues and endings to the star's life. A supernova is one, and that is where we get an explosion. And so in this explosion, what we generate are a lot of neutrons. We're essentially just crunching everything together under high temperature and pressure under this implosion. And so we have our core of iron 56, and it essentially falls apart. We create some helium, and we create neutrons. Again, this is just an example. There's probably many different pathways to this. The helium in this scenario will then start to form more neutrons and protons. The protons react with electrons to form even more neutrons. What you see here is during this implosion, due to gravity, is we're essentially getting back to those elementary particles that we started with in the Big Bang. These neutrons are what then react with heavier elements that are still present in this implosion, then explosion. And during this time, these neutrons are embedded into the nuclei, creating the heavier elements, and then many of those elements are not stable. You've just injected neutrons into these nuclei. They're not necessarily stable. And so in the end, what we'll talk about is how we get to the elements we have on the periodic table. So in the paper that you've read, it talks about the sea of instability. This plot has protons plotted against neutrons and shows all the different possibilities in terms of the number of neutrons, the number of protons in a nucleus. But the only ones that are stable are in that peninsula. Those are the elements that we observe in nature and what we primarily see on the periodic table in terms of the masses. Also note, the paper didn't talk about the island of stability. So beyond the peninsula, we see an island. That is a theoretical value that has not yet been reached, I do not think. So at any rate, this is kind of where we're going with this formation of the elements. So these neutrons that are created during this process, they become embedded in nuclei, making the heavier elements. However, most of these elements that are produced in this stage are unstable. Unstable is another word for radioactive. So these elements then have to end up decomposing and going through this process of decay until they form a stable element. And this is just a natural process that continues to this day in terms of radioactive material. And so, again, during this explosion, we get neutron capture. All these neutrons are produced. They go into, say, a element that's present, and that neutron shows up in the mass of the new element. So remember when we first started to talk about these nuclear equations, I said that the top was the mass, the bottom was the charge. It still holds true, but at this point, the way we're going to think about it is the bottom number is the number of protons, the top is the number of protons plus neutrons. So the top number is neutrons plus protons. The bottom is number of protons, or we could say, using the periodic table, the atomic number. So here we're capturing a neutron, forming a heavier element. Over here we have beta decay. Again, this element here is not stable. It's radioactive. Therefore, it decomposes, and it does so by releasing an electron or ejecting an electron from the nucleus. When this happens, what's really going on is, if you notice, this bottom number changes from 26 to 27. And that is because we're trying to balance this reaction. Essentially, what is happening is one of these neutrons that are being captured decomposes into a proton and an electron. Because you see, we gain a proton here, but we keep the mass to be the same. So under beta decay, that is what is occurring. A neutron is changing to a proton, and an electron is being ejected. So you should be able to write these types of reactions. And so that was discussing the R process, which is a rapid process which happens during the implosion and explosion. The S process is also discussed in the paper I put out. And so this process is very similar to the R process, but it doesn't happen in an explosion. It happens over billions of years within the red giant. So within the red giant, there is iron, there are neutrons, there are lots of different particles and elements. And over time, we can slowly piece together heavier and heavier elements from this. And so looking at the sea of instability and that peninsula, essentially over these billions of years within the red star, we can slowly create stable elements, and we do so up into bismuth 209, which is at the very end of the peninsula. If we look at a periodic table, that is the last stable nucleus. Anything heavier than bismuth, bismuth is right there. Anything heavier than bismuth is radioactive, period. So with that, we'll finish this video by just summarizing the life and death of a star. So let's wrap up this topic and kind of summarize what we've been talking about in terms of the formation of the elements. So we started with some cosmic dust, which coalesced under the influence of gravity. It became pressurized, temperature increased, the temperature got hot enough where that dust actually ignites and we get a star. So this is much like our sun in terms of it's a fairly new star, and it is currently creating energy by um, turning hydrogen or burning hydrogen and forming helium. And this is occurring at about 10 to the 7, 10 to the 8 Kelvin. And so the expansive force that is keeping this star going and counterbalancing the contraction due to gravity is this heat from this fusion reaction. So these are exothermic reactions that are occurring. This will happen over many billions of years as it ages. And so we're here, and over time, over billions of years, the hydrogen fuel will slowly run out, and then the star will start to collapse because there is not enough expansive force. And during that collapse, the temperature will increase, which will allow conditions so that we can now start fusing helium nuclei together to form heavier elements, and that we can do until we reach iron 56, which then starts to collect at the core of a red giant. So that red giant, according to your paper, will continue to age. There's another stage called a red supergiant, and that is just at the latter stage where we're still burning helium, but we're also using heavier elements up to iron 56 at higher temperatures to continue to combat the contraction due to gravity. So this star is just trying to stay alive. So at this point, depending upon the size of the star, so if it's greater than 10 times the size of our sun, that scenario likely leads to a supernova. Now we're interested in this scenario because this gives life to our solar system. So during the supernova, we get a core that implodes, creating all these neutrons, and then we get an explosion. And within that explosion, we have all of the elements that we see in our solar system. So our sun is actually a second generation star. It is from the remnants of a supernova from a first generation star, and all the planets are this debris. And this occurs through the R process. And I should have said somewhere in here that this is where in here we get the S process. Another note, if you look at the notes, I have R process written right here between the young star and the red giant. That is not correct. So I don't know how that got there. So there is no R process at the beginning. The R process happens very rapidly in the supernova. S process happens in this stage where we are able to create heavier elements slowly. And so again, from this supernova process, we get essentially the abundance of all the elements in our solar system. And again, depending upon you know, the formation due to fusion, we get a lot of things like carbon and oxygen and magnesium and iron. But there's other areas where we also get heavier elements and difference in relative proportions. But you can look at this again in the paper that you read. I also wanted to bring up, how do we know how much of these elements are in stars? And when we look through a telescope, how can we see and measure the abundance of the elements? Well, I want to remind you that every element has a very unique fingerprint in terms of its spectra. In the atomic state, all of these elements get excited and release energy through their quantum states, their energy states. And depending upon the size of the nucleus, these quantum states, these energy states, are all different. And so every single element has a beautiful fingerprint of light spectra, and we can measure this with telescopes. You have to keep in mind that a lot of these spectra are shifted towards the red or the blue due to the Doppler effect of light, but nonetheless, they can make those corrections and they can figure out how much hydrogen, how much helium, how much oxygen is in a star, you know, millions of light years away. And lastly, in terms of the PowerPoint, just look at this figure 2. This shows the abundance of the elements on Earth, which, you know, is a little bit of a filter given that we have quite a few planets, and that some of the heavier elements ended up in, you know, the first 4 planets, Mercury through Mars, and then lighter elements are in the larger gaseous planets, starting with Jupiter. But nonetheless, we kind of see our makeup. And if you look at the relative mass numbers of these, a lot of them are even numbers of 4, like 40 and 20 and 16 and 56, things like that. So 24 for magnesium, I believe. So all from the fusion of helium in a red giant. So lastly, the other scenario is if we have a red giant that is somewhat small, less than 10 times the size of our sun. We can create a white dwarf where 1 cubic centimeter weighs about 100 tons. So it just kind of crunches, and that's the end. We could also have a black dwarf, which is a cold chunk of ash. We could create a neutron star, which is for a size of a star that's 1.4 times the size of our sun. In that case, we end up with just a round ball of neutrons, and it's extremely dense, 40 million tons per 1 cubic centimeter. And lastly, if we have something greater than 3 solar masses, there is a possibility that during the implosion, you'll actually rip a hole in the space-time continuum, and you can create a black hole. So those are all the possible scenarios in the death of a star. So I hope you enjoyed this video, and I look forward to your questions.